Alright, hell yeah. Now welcome back. Now this is the mold effect. And I just thought of something, so we, you know what I mean? These are the thoughts we're going to go over, maybe hopefully a short video. But anyway, you got the ball chain. The first thing I want to show is like, okay, you have a huge mass. Let's say you just dangle the ball chain. It's got no velocity. And you just dangle it, and then you have the pile of ball chain in here. Is the force on this lip going to be equal to the mass of this ball chain times gravity? Kind of that mg, you know what I mean? Mg in the downward direction. I think it is the second you let go. You know what I mean? You might have to hold this cup because, especially if you got a big old lip, it's like maybe it'll tip it over. But now I'm saying, you know what I mean? The second you actually do let it go, and it actually picks up velocity upon velocity because of the gravity, then it's going to be negligible, and we'll take a look at that. That's why we do this more technical. We'll kind of do this last. But if we just have a piece of ball chain and we're hanging onto it right at the top, sure, on our fingers we're going to have to hold it with the tension mg. And basically the tension right here in this little part of the rope is going to be the mass of this entire, basically the entire chain. You know what I mean? That's kind of, if I popped up a thing like there and held onto it, it'd be the mass of everything. Now, if you held it right here, it would just be the mass of this. So even if I'm holding it right here, sure. And this isn't even what I was getting into. But yeah, the mass of, the tension in this string is only due to the weight of that ball. Got it. But anyway, we're interested right at the top. So if we hold the ball chain right at the top, hell yeah. The tension right here, let's say it's just right here, is going to be all this ball chain. So, you know what I mean? Because we set up a free body diagram of the actual ball at the top. We set like a 60-degree angle pulling it this way. We call this huge because we got all the ball chain that way. And we call this small. But in essence, you have to add them together. So the normal force, you know what I mean, in this direction, the normal force is up. It has to be the same as the ones down. So if you have a big mg down, a big tension due to mg, and then you'll have a small one over there. But these are additive. So you'll have a huge normal force. You'll be holding, like the second you let go, there'll be so much force right on the lip of this. You'll have to hold the container, you know what I mean, from tipping over, stuff like that. We got it. Okay, but now what I'm showing, what I'm going to prove to show is that once you let it go, this gets reduced to negligible. Anyway, but anyway, we want to look at the other component in the other direction, but we're going to look at that last. That's just giving you a little taste of the future in a couple minutes. Am I even recording? Hell yeah. Alright, so let's throw some more time on the clock. Alright, heck yeah. And so here you go. So yeah, like I said, I'm holding this ball chain, there's tension. Got it. The second I let go, guess what happens? No tension. It's a free-falling system. There ain't no tension in this rope. So think about that. So the second you let go of this system, is there tension in the rope? Well, let's just say there isn't, but you do have this component in the chain. So it's way less than actually holding it, and it's way less than the initial condition of being like, okay, I'm going to drop the ball chain, how much tension is on there? This is going to be max, but the second I drop it, yeah, this tension gets reduced because of gravity. Okay, any other questions to ponder? Now let's flip it over. Okay, I want to do a water experiment. I want to take like that thin, you know what I mean, it's like thin tube that once you put water into it, it can get bigger because it's just flexible. But it'd be interesting to put it, because here's kind of this scenario of the ball jar. And then have it kind of go up over a dowel here and then up over the dowel there. Okay, so the thing with this is now you got water flowing through here. So we're going to just use this because it gets our mind wrapped around what's happening. There's a lot of weight of water, you know what I mean, in this side of the tube. It's pulling down on the tube. We got that. But in essence, it's still also in free fall, mg. You know what I mean? We got some velocity pumping through here. So yes, it's interesting how, yes, you do have a huge weight over here, but I still think you would get the same mold effect. You would, because it's flexible, you would get this tube to pop up and ride up. But I don't know. You know what I mean? Instead of just quickly going around, you know what I mean? I mean, let's say this stuff actually does have a bend radius of like 4 inches, and then this is 4-inch PVC. You know what I mean? Is it just going to suck up to the PVC, or is it actually going to levitate? Could it hold its arc? And I think we kind of know that ball chains like to hold their arc, and so now we're gonna look at that and why. Okay, so if you have a ball chain resting on the table, what and this gets back to what we're going to try to prove with this equation is you have definitely a weight of ball chain hitting the ground and pulling it down. So when this in the ball chain right here, velocity is 0. But at some point, and this is just going to be velocity of the rope. I just call it velocity max. I think that's good because it's a constant velocity. But at some point, this part of the rope, whether it's a rope or ball chain, is going to get up to velocity. And, you know, is it going to just go down the lip and just follow it? Well, one, sure, because this is so heavy. You know what I mean? Due to continuity, it kind of has to follow this path. Because it's weighted down. Like the second it wants to go maybe past this lip, it's instantly kind of getting pulled down into this long line of ball chain or a rope or whatever. But what I want to show is that... I want to show this. Yes, you do have a velocity here of things wanting to go down, but this becomes a constant, and you have a huge velocity with a lot of rope. And what happens here is that, like, even right here, this velocity is 0, but this velocity right here, now this isn't really what I wanted to talk about, but this is kind of the idea of how a ball chain works. Let's get more time on the clock. Is you do have kind of like a whipping motion, you know what I mean? Let's say there's no velocity right here. Velocity is 0, but right here, velocity is max. You know what I mean? So, and it's going to take all this, it's going to take this section of rope and get it up to speed. Well, if it's going to do that, if it's going to change its velocity from 0 to max, that's a huge acceleration, and you're going to get a whip effect. And the only way to actually follow continuity, you know what I mean, because it can't push on this rope, you know what I mean. This is just, it's maxed out, and because it can't add velocity to this, the thing's going to get whipped out and over, and it's going to get a. Put it this way. I think this is because that's why I'm trying to do this. Is just like, we'll prove it. So yeah, let's say right here there's velocity 0, and then right here there's going to be 0 velocity from here to here, and it's max. And you're trying to get this little piece of rope up to max velocity. Oh shoot, I had it. Anyway, I might have to pause the camera just for a second. All right, hell yeah, this is kind of where I get into a loss. But, you know, what I want to show from the other perspective is that you're going to get this piece of rope to go this direction, you know what I mean, and due to continuity. And let's say even this to here, this is a very short section of rope. Let's say you wanted to increase the velocity of this, or is it slowed down? I don't know, but it's just the difference of like, hey, this rope can be out here, or it can be nice and tucked in. And, yep. And then here, you know, I said Norway, you know what I mean? The distance between point A and B on a coastline of Norway, I don't even know if Norway's the country, but it's just way huge. So, it's just something that if you have continuity of something going from A to B real fast, but you need to, like if this is it. So if this is Vmax, you know what I mean? If your rope's going Vmax here, but you have an incoming velocity of Vmax plus, you know what I mean? It's a higher velocity, then yeah, then this rope's gonna go up, you know what I mean? And maybe do some of these sine waves before it actually gets Yeah, because if you have a higher gradient in this, all it has to do is just take a longer path. And then if it takes that longer path, this is still Vmax. Even though you got Vmax plus coming in, right here, this rope is just seeing Vmax. And then so that's kind of what's going on with the ball chain. You're having this driving force to whip out sections, and this is kind of what's happening. You're getting a higher speed here. This is Vmax plus, but because it takes the shape of a longer shape, then that's going to equal this Vmax. And anyway, and just some questions. Let's go over this. Does the velocity become more constant when the ball chain hits the ground? Because you have this mg, you know what I mean, ball chain wants to fall due to gravity and get faster due to gravity. The second it hits the ground, this is just a question for me. Does the velocity, is that where it hits Vmax? Like, is it already at its max and actually it slows down or speeds up? Or yeah, does it actually get constant? And what I think what happens is once the ball chain hits the ground, if there's any gradient, if like right here is Vmax, and then right here is this is Vmax plus, and this is Vmax, and this is Vmax minus, I think once it hits the ground, you get a continuity. So I'm thinking there's a continuity in velocity where you can just call it all Vmax. I think that's what's going on there. All right, mass and orbit requires a force. This is interesting, yes. So if you do have a mass that's in orbit, it has to have some sort of force back to the center. I mean we're talking, let's say this is the sun and this is the earth. Well, due to the gravity of the sun, it's always like bringing it back. The sun, I mean, the earth just wants to go this way at like a really high velocity. But because it's being pulled back to the, it should be here, but because it's being pulled back to the sun, it's here. Okay, we got that. More time on the clock. Now, I just reversed that. Like I said, well, let's reverse that. And it's not really reverse that. It's like, hey, let's say this is the orbit of the Earth around the sun. Got it, got it. And now let's say, for whatever reason, the Earth, like in its orbit, just goes hella faster. You know, 10 times faster, 100 times faster, V100. Well, guess what? The orbit of the Earth is going to be way out here because this force is due to inverse distance squared. You know what I mean? But anyway, so that's what happens if you increase the velocity. So we have a velocity to v100. You increase the distance away, you know, from the center. Now with gravity, yeah, that's the equation. We get it. Gravity is still affecting our same mass, but it's just going to be farther away. And then how does that relate to us? Well, it's like I'm showing that there's, and I guess I'm just calling it a faster velocity, like a whipped velocity. There's a faster velocity of this right here. The second this goes from V0 to V something, it's going to be greater than this constant velocity in the rope. That is what I am assuming, because that's the whip effect. And the reason why you can assume that is, let's take just the last bit of rope, hardly has any mass negligible, and then we have this huge system that has a huge mass, and it's got a big velocity. And guess what? It's acting on a small mass, and all of a sudden, within a small change in t, this crap went from velocity 0 to velocity hella. And because its mass is so small, the velocity hella, there you go. And because you have continuity, same thing. This gets whipped this way, but it's still attached to this, and obviously this is going to find its way back to here. And then so there you go. So this change in distance due to a loop is going to make up for the continuity of velocity hella. Because if you got, same thing from the Norway analogy. Where the hell was that? Hell yeah, you got velocity max coming in. Well, yeah, you got velocity max plus coming in. Well, sure. Now this is velocity max because we continuity. I was gonna, you know, make that word. Continuitized it. All right. So we got one more thing to look at, and that's this free body diagram, and then we'll try to make this video under 30 minutes. More time on the clock. All right, hell yeah. So what the hell is a free body diagram? It's where you throw a chunk of mass, that's going to be right here, and it's going to have a little mg. I said it was negligible, but we need it because we have a normal force. Well, I mean, no, it's not negligible. It's negligible for the forces in the y direction. So this is the forces in the y direction. You have a normal force pushing up. Now, if this was just a rope going over, or a wire, if this was just a wire, you'd still have a force here, but it has to equalize this force. This is T small because the container's pretty short, and this is T huge because you got it all the way to the floor. All right, this is a 60-degree angle, so this is just going to be 0.5% or 50% in this vertical direction, 86% in that direction. But anyway, we only need it in this direction for the first part. And yeah, so these are going to add. They're just going to be additive. So it's basically the whole weight of the chain. The whole weight of the chain right before starting is going to be the weight on this one ball right at the lips. That's what we're looking at right there. Got it. And then there's no acceleration in the downward direction due to continuity because you have the lip. It can't go down. It can't go. The only direction it can go is that direction. Got it. Okay, so now you do the forces in the x direction. Forces in the x equals mass times acceleration. So we add up all. So in this, the mass was this ball. The acceleration, there was no acceleration in the y. And there you go. But now in the x direction, there is no normal force. There is no normal force. So now you just have the tensions, which are the same. This one's huge. Look at this. It's tugging a war huge that way, small this way. So this thing is unbalanced, right? It's unbalanced. There's a huge force this way, not force this way. So if you have unbalanced force, that's motion. That's acceleration, change in velocity. So this thing had velocity 0 right at the start. Well, now it's going to have velocity hella that direction. And that's what we call acceleration. So if we look at this, it's pulling this way. Oh, it's not 0.5 because in the x direction, well, the y direction, no, the x direction is like 0.86. It's sine 60, cosine 30. Okay, so it's like 0.86 or something. You know what I mean? You do you. But yeah, 85%. So 85% there, 85% there. So you have 85% of a small pulling this way, and 85% of a huge pulling that way. And that's why you have it equal to the mass of the ball times the acceleration. So this acceleration is going to be huge because this is huge and this is negligible. So now you have a huge tension this direction. Well, that's why we have Newton, because he says if you have a force in just one direction, well, guess what? You know what I mean? You're going to see an acceleration. Why don't we see an acceleration when we're just standing on the earth? Is because we've got a normal force. It equal and opposite. Our mg down is our weight. Normal force is popping up. We ain't falling into a hole. The second we jump into a hole, guess what? This normal force, it goes away. It goes away. You're going to be falling mg style. All right, so anyway, more time on the clock. Alright, so this pretty much wraps it up, is that you have a hella acceleration. And if you haven't already said, due to continuity, this thing can't go down, you know, because it's on the lip. So even with the initial condition of this thing rattling out of the hole, you know what I mean? Well, obviously, and then here's the other ball right there. And then let's say, and this is, and like we said, this is trapped in just V max. You have V max generating, mind you. Whoa. Well, if it's just starting out, I don't know, maybe there's no velocity either. There's no velocity on that one. We're just picking this one. But what I'm showing is that even this one, the velocity of this one is going to be more down. The velocity of this one is going to be more down. The velocity of this one is going to be hella in this direction. And if it's hella in this direction, it's going to be over here. And even just being over here before it actually falls down this continuity, you know what I mean, funnel, makes a small loop. So even that would be the Mould effect right there. Due to continuity, there you go. There's the Mould effect. And this effect just takes over the more that you have a whipping force taking a small pile of mass, freaking whipping it. And the reason this works is because this is a change in direction. Like, let's say this ball was just hanging, you know, just off a ceiling, and then you got this whole thing in motion. it would just fall. But the crazy thing is, let's say, for whatever reason, I mean, this is why you can do this. You could have one ball right on the ceiling, taped to the ceiling, and this is an experiment I want to do. Take a chain whip, or a ball chain, and then drop this side. Because the second you drop this side, all these balls will have Vmax. The second this one goes taut, all these balls have Vmax except this one. The moment before this one gets ripped away, its velocity is 0. And guess what? Its velocity is hella small. But guess what? This whole ball chain is hella fat mass. It's got velocity max, fat mass, and it's got an equal tiny mass. Velocity hella. So this ball, with the slow motion camera, would go in front of all the other balls. And I do want to do that experiment. I can do that experiment right now. That's why I'm doing this, because I want to get more just hands-on approach to the ball chain fountain. You know what I mean? Whether it disproves it or not, you know what I mean? It's just really good to get these intuitive things instead of just throwing jumping beans. You know what I mean? Because this is still jumping. I love this. You know what I mean? The fact that you're taking this with a huge velocity from velocity 0 to Vmax, and then you can do that with the ball chain. You can take this and it'll pendulum all the way up to here, and it'll still have some velocity max in this direction, in the Y direction, and it'll have velocity max in the X. Who cares about that? But this velocity max in the Y will impact this mass. So now if this is connected to the whole ball chain, hell yeah, it accentuates. So you do get this. You do get your huge M, Vmax, you know, equalizing a tiny m, and that means velocity hella. And then, so I do credit the ball chains for having, you know, a ball, a stick, and a loop, and another ball, because you can get a pendulum effect out of the container of the ball chain, of the container. Alright, so that's for another video, but I'm glad I inserted that in here. Hell yeah, this is like part 4 or 5, you know what I mean, of doing the ball chain. And anytime, you know what I mean, I got an idea rolling through my brain, I love it. I love putting it to paper. We did a real good job on this one. Did a real good job. Alright, thanks for joining me, and guess what? That's a video.